Hi, we'll be back to your regularly scheduled program in a minute, but first, is your stock car moving too slow for your liking? Are you not getting the speed you need during your races?
Change track, which means green flag racing finally for the banners. They've been waiting a while. Here we go.
Then look no further than trigonometry.
Hi, I used to not get the speed I needed, but by using trigonometry, I've gotten faster and faster. Using trigonometry, I figured out the most beneficial line to my car. I picked up 1.5 seconds at Wake County Speedway.
Wow, 1.5 seconds per lap is a lot. In fact, you can use trigonometry to see how fast you're going, your line around the track, your weakest points, and how to improve all of it. We're going to talk about the basics of trigonometry and how to apply it to your car.
First thing you need to know is the basics of triangles. We need to know how to find the side lengths of 30, 60, 90 triangles, 45, 45, 90 triangles, as well as how to use sine, cosine, and tangent. With this information, you can really pick up some speed. To find the missing sides of 30, 60, 90 triangles is fairly simple. X is the opposite of the 30-degree angle, which means that the 30-degree angle's two lines extend out, and whatever connects them is the opposite side. The second side is x times 2. That's the hypotenuse. The third side is x times the square root of 3. Remember, x is always the opposite of the smallest angle, or 30. Next, we have 45, 45, 90 triangles. To find the side length, the two legs, or these two bits here, which are touching the 90-degree angle, are x. They're both the same. The final side is x times the square root of 2. Sine, cosine, and tangent are less simple. First, you need to know when to use each one. Use SOHCAHTOA to figure out which to use. You can remember this with the phrase, "some old horse caught another horse taking oats away." Speaking of horsepower, you can get the most out of your engine's horsepower by taking the best line. This means use sine if you need the adjacent, cosine when finding the opposite, and tangent when finding the hypotenuse. The formula for each of these is sine when you have the opposite and the hypotenuse, cosine when you have the adjacent and the hypotenuse, and tangent when you have the opposite and the adjacent. When you're using sine, place the opposite side's length over the hypotenuse's length. Cosine is the adjacent side length over the hypotenuse length. Tangent is the opposite side length over adjacent side length. Fairly comprehensive. Now for the inverse. Inverses are used when finding missing angles. If you know two sides but not an angle, you'll take the power, or the function rather, and raise it to the power of -1. This will make it inverse. To use it, simply place this, or sine to the power of -1, or inverse sine, inverse cosine, inverse tangent, and multiply it by whatever the two sides that you do have to find the angle. You're still going to use the same sides as though you were using SOHCAHTOA. So if you're using inverse cosine, you're going to use the length of the adjacent over the length of the hypotenuse times inverse cosine. Finally, let's apply this all to stock cars. If you use a function that you now know, such as cosine or tangent or 30, 60, 90 formulas, you can find how fast you're going, distance between each of these points, and, well, how fast you're going around a track. All you need to do is measure the distance between the wall of the track and the point where you got your data from. Then measure this against the next point of data. This gives you two side lengths. This is always going to be a 30, 60, 90 because, well, that's how I set it up. So all you're going to do is find the distance of this hypotenuse, and now you've got the distance between the wall and how close you need to be getting from this point to the wall. It doesn't make much sense, but I'll try my best. Basically, when you're coming around the track, you want to get as close to the wall as possible. So as close to this wall as you can possibly get. This isn't the most accurate example. When I'm actually here, I'm fairly fairly, 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 close to the wall, as in a couple feet away at most. But for the sake of this argument, we're going to say that we're this far away. This distance gives us how far I am from this point here to this point here. So that's how far I'm going. What I need to do is take this point and rotate it down without hitting the hypotenuse on the curve of the wall. This will give me how close I can get to the wall without actually hitting it. This will change it from a 30, 60, 90 into a different triangle, maybe a 74, 60 something. Then, when I come around the track on my next lap, all of these dots, by the way, are different laps. When I come around next, I'll take that angle. Maybe I'll get faster. Who knows, maybe I might even get slower if I'm not driving as well as I should be. You can see in this clip that as we come around the corner, the number 3 car is much farther ahead of me, number 4. But as we come around the corner, I duck underneath him using those angles we were talking about, allowing me to pass him and eventually finish the race ahead of him.
So the next time you have a need for speed, why not be the smartest driver on the track and use trigonometry for the win?